Imagine the universe, a vast expanse of mysteries waiting to be unraveled. This colossal space, infinitely complex, is filled with galaxies, stars, and phenomena that boggle the mind. The universe presents us with an endless array of questions, each more intricate than the last. And yet, the goal of science is to comprehend these enigmas, to make sense of the inscrutable. To decode the universe is to decode existence itself. Science's quest to comprehend this cosmic puzzle leads us to the theory of everything. Delve into the world of the incredibly small, the realm of quantum mechanics. This is a landscape where the rules of classical physics are thrown out the window and particles dance to a different tune, a tune of probabilities and paradoxes, where nothing is as it seems. In this realm, particles exhibit a dual nature. They can behave as particles, yes, but also as waves. This is known as wave-particle duality. Imagine throwing a tennis ball against a wall. You'd expect it to bounce back, right? But in the quantum world, there's a chance, a small one, but a chance nonetheless, that it could end up on the other side of the wall. This is known as quantum tunneling. Now let's talk about Heisenberg's uncertainty principle. It tells us that we can't know both the position and momentum of a particle at the same time. The more precisely we measure one, the less precisely we can know the other. It's not about the limits of our measuring tools. It's a fundamental aspect of nature. Then there's the concept of superposition. A quantum particle doesn't settle on a state until it's measured. Until then, it exists in all possible states simultaneously. It's like having a coin that's both heads and tails at the same time until you look at it. And let's not forget about entanglement. Two particles can become entangled such that the state of one instantly affects the state of the other, no matter the distance between them. This defies our everyday understanding of space and time. These are just a few examples of the mind-bending principles that govern the quantum world. They challenge our everyday intuition and force us to look at the universe in a whole new light. It's a world that's strange and counterintuitive, and yet it's been proven time and again by experiments. Quantum mechanics, a science of probabilities, challenges our understanding of reality. And as we continue our quest to understand the universe, the quantum realm remains a fascinating and fundamental part of the puzzle. Now, ascend to the grand scale of stars and galaxies with Einstein's theory of general relativity. This theory, born from the brilliant mind of Albert Einstein, proposes a revolutionary concept. Gravity is not simply a force, but a distortion of space and time, or space-time, around massive objects. Imagine a bowling ball placed on a trampoline. The weight of the ball causes the trampoline to curve, and any marbles placed on the trampoline will roll towards the bowling ball. This is similar to how general relativity describes gravity. But let's dive a little deeper. In the universe, the trampoline is our space-time, a four-dimensional fabric that includes 3 dimensions of space and 1 of time. The bowling ball? That's any massive object like a planet or a star. The marbles are smaller objects like asteroids or even light, which follow the curves created by the bigger objects. This concept is a stark departure from Newton's law of gravitation, which treats gravity as a force between 2 objects. Instead, Einstein's theory tells us that massive objects deform space-time around them, causing other objects to move along these curves. Yet, general relativity isn't just about gravity. It's a theory that describes how the universe works on a grand scale. It explains phenomena like the expansion of the universe, the existence of black holes, and even the bending of light around massive objects, a phenomenon known as gravitational lensing. Impressively, despite being over a century old, general relativity has stood the test of time. It has been confirmed by numerous experiments and observations, from the precise timing of GPS satellites to the detection of gravitational waves, ripples in space-time caused by the collision of massive objects like black holes or neutron stars. General relativity paints a picture of a universe woven into the fabric of space-time, a universe where space-time tells matter how to move, and matter tells space-time how to curve. It's a beautifully intricate dance of cosmic proportions, a testament to the elegance and complexity of the universe we inhabit. Quantum mechanics and general relativity, 2 brilliant theories, yet they clash. This paradox forms the crux of what we call the problem of quantum gravity. On one hand, we have quantum mechanics, the theory that governs the world of the very small, atoms, particles, and quarks. It thrives on probabilities and uncertainties, with particles popping in and out of existence like elusive phantoms. On the other hand, we have general relativity, Einstein's brainchild, ruling the domain of the very large, stars, galaxies, and the fabric of space-time itself. It paints a picture of a universe that is smooth and continuous, where massive objects curve space-time and create what we perceive as gravity. So, where's the clash? Well, gravity, as defined by general relativity, is smooth and continuous. It's like a gently rolling ocean wave. But quantum mechanics says that at its most fundamental, the universe is made up of discrete, individual packets like grains of sand. Trying to reconcile these two pictures is like trying to make a smooth beach out of grains of sand. It's a conundrum that has stumped scientists for decades. If we apply quantum mechanics to gravity, we get infinities that make no sense. If we apply general relativity to the quantum world, the smooth fabric of space-time breaks down into a frothy mess. These conflicting theories are like two beautiful symphonies, each playing in a different key. Individually, they're masterpieces, but try to play them together and you get cacophony. Scientists have been trying to retune these symphonies, searching for a new theory that can harmonize the quantum and the cosmic. A theory that can describe gravity in terms of quantum mechanics, a theory that can explain everything. The quest for a theory of everything is the quest to harmonize these opposing symphonies. It's one of the grandest challenges in modern science. And as we delve deeper into the mysteries of the universe, we're getting closer to finding the melody that unites it all. Enter string theory, a potential bridge between the quantum and cosmic realms. This is where things get really interesting and perhaps a bit strange. String theory proposes that at the most fundamental level, all particles aren't zero-dimensional points, but rather one-dimensional strings. This theory radically suggests that these infinitesimally small strings vibrate at different frequencies, and these vibrations give rise to the diverse particles we observe. Imagine a violin string. When you pluck it, the string vibrates, and it's these vibrations that create sound. Similarly, in string theory, the universe is like a symphony of strings, and the laws of physics are the laws of harmony that these strings obey. The particles we see, such as quarks, electrons, and photons, are simply different notes on the string. But where does gravity fit in? Well, string theory elegantly incorporates gravity by introducing a new particle, the graviton, a string vibrating at just the right frequency to interact with space-time itself. This is a monumental shift in our understanding, as it suggests that gravity isn't merely a force, but a result of these vibrating strings interacting with the fabric of the universe. Now you might be wondering, if string theory is so revolutionary, why isn't it universally accepted? The simple answer is that it's incredibly difficult to test. The strings are so minuscule that they're far beyond the reach of any current or foreseeable technology. And there's another twist. String theory requires the existence of extra dimensions, up to 10 or 11, far beyond the 3 dimensions of space and one of time that we're familiar with. Despite these challenges, scientists continue to explore string theory because it offers a tantalizing possibility, a unified theory of everything. It's a theory that could potentially marry the microcosm of quantum mechanics with the macrocosm of general relativity, providing a comprehensive understanding of the universe's fundamental laws. String theory could be the key to deciphering the universe's ultimate mystery. It's a grand symphony waiting to be fully understood and appreciated, a cosmic concert playing out across dimensions and vibrating at the heart of reality itself. The theory of everything remains elusive, but the pursuit for understanding never ceases. Imagine our universe as a grand cosmic puzzle, and scientists, they are the relentless puzzle solvers. Each fragment of knowledge, each scientific experiment, every mathematical equation we solve brings us one step closer to seeing the bigger picture. Today, in laboratories around the world, researchers are hard at work, striving to unlock the mysteries of the cosmos. They're testing new theories, challenging old ones, and always seeking to expand the boundaries of our understanding. They're probing the depths of quantum mechanics, exploring the vastness of space-time, and even trying to catch the elusive strings that might underpin everything we know. But why this relentless pursuit? Why this ceaseless curiosity? Because that's the heart of science. It's the insatiable desire to explore, to understand, to discover. It's about asking questions and never settling for the status quo. It's about pushing the boundaries of the known and stepping into the unknown. Science doesn't have all the answers, not yet. But every question we ask, every experiment we conduct, every theory we propose brings us closer. Closer to understanding the fundamental laws that govern our universe, closer to unveiling the cosmos' deepest secrets, closer to the theory of everything. In the quest to understand the universe, every step forward brings us closer to the theory of everything.